Hey everyone, welcome back to the channel. So, you want to build an operating system? That's awesome. It's a seriously ambitious project, not gonna lie, but crazy rewarding. We're talking about the core software that controls everything your computer does. No big deal, right? This isn't going to be some hand-holding tutorial, though. We're diving deep into the guts of your machine, learning how to write code that talks directly to the hardware. You ready to get your hands dirty? Let's get started. Alright, first things first, you can't just jump into this blind, you've got to come prepared. We're talking about understanding how a computer actually works at a fundamental level. Think of it like this. You wouldn't try to rebuild an engine without knowing what a piston does, right? So before we write a single line of code, we need to talk about the essential building blocks. We're going to need to get comfortable with low-level programming languages. And when I say low-level, I mean about as close to talking to the hardware directly as you can get. C and C++ are your best friends here. They give you the fine-grained control we need to interact with memory, hardware, and all the nitty-gritty details that make an OS tick. Next up, computer architecture. We need to understand how the CPU, memory, storage, and all the components in your computer talk to each other. Think registers, memory addresses, buses, the whole shebang. This knowledge is crucial because we'll be writing the code that manages all of it. And hey, let's not forget about data structures and algorithms. We'll be dealing with lots of data, so organizing it efficiently is key. Stacks, queues, linked lists, these are your tools for keeping everything running smoothly. Oh, and concurrency. We need to make sure our OS can handle multiple things happening at once, like running programs and responding to user input. Finally, we need to understand the boot process. That magical moment when you turn on your computer and it springs to life. We'll be writing the very first piece of code that executes the bootloader, which then kicks off the whole OS loading process. Okay, we've got the theory down, time to get our hands dirty. But first, we need the right tools for the job. Building an OS isn't exactly drag and drop programming, you know? We're going old school, down to the metal. First up, the cross-compiler. See, the code we write for our OS needs to be understood by the bare metal, no fancy operating system to help us out here. A cross-compiler lets us write code on our regular computer that can be run on our target hardware, even if it's completely different. Next, we need a virtual machine or an emulator. This is our playground, a safe space to test our OS without risking turning our main computer into an expensive paperweight. Think of it like a digital sandbox where we can experiment without fear of breaking anything important. And of course, no programmer is complete without their trusty text editor or IDE. This is where we'll be spending most of our time, writing, debugging, and cursing at the code. Pick one that you're comfortable with, because we're going to be writing a lot of code. We'll also want to grab a hex editor. This will let us look at the raw binary data of our OS, which is super helpful for debugging those really weird issues. Remember, setting up your development environment can be a bit of a pain, but trust me, it's worth it. Once you have everything up and running, you'll be ready to start building your very own OS. Alright folks, it's time to write some code, but hold on, before we get to the fancy stuff, we need to create a bootloader. Think of this as the tiny program that kicks off the entire OS. It's the first thing that runs when your computer wakes up. We're talking bare bones here, people. The bootloader's job is simple. Initialize the CPU, set up the memory, and tell the computer where to find the kernel, the heart of our OS. We're talking a few hundred lines of code, max. It's a delicate dance, but once you get it right, it's incredibly satisfying. Now, we can write our bootloader in assembly language, which is about as low level as it gets. We're talking directly manipulating registers and memory addresses. It's hardcore, but it gives you an amazing understanding of how the CPU works. Or, if assembly feels a bit too intimidating, we can use C. It's a step up in abstraction, but still gives us the control we need to get the job done. The key here is to keep it simple and focused. The bootloader has one job, and one job only: load the kernel. Once we've got our bootloader written, we need to flash it onto a bootable medium, like a USB drive. This is what we'll use to boot up our OS for the first time, and let me tell you, seeing your bootloader run on real hardware is an amazing feeling. It's like watching your baby take its first steps. Okay, we've got our bootloader up and running, which means it's time to tackle the heart of our OS, the kernel. This is where things get really interesting, and trust me, we're going to be here for a while. The kernel is the core of the operating system. It's responsible for managing the system's resources and providing a platform for applications to run on. We're talking memory management, process management, file systems, and a whole lot more. First up, memory management. We need to make sure that every program running on our OS has access to the memory it needs, without stepping on each other's toes. This involves setting up virtual memory, paging, and all sorts of fun stuff. It's complex, but it's what allows our OS to run multiple programs at the same time without crashing. Next, process management. We need to be able to start, stop, and manage all the different processes running on our system. This involves creating processes, scheduling them to run on the CPU, and handling communication between them. It's like being the conductor of an orchestra, making sure everything runs in harmony. And of course, we need a file system. This is how we'll organize and store data on our hard drive. We'll need to implement things like file creation, deletion, reading, and writing. Without a file system, our OS wouldn't be very useful, would it? Building a kernel is like building the foundation of a house. It's a lot of work, but it's essential for everything that comes after. So take your time, break the problem down into smaller pieces, and don't be afraid to ask for help. All right, we've got our kernel up and running, which is awesome. But right now, it's kind of like a car without a steering wheel. We need a way for programs to actually interact with the kernel, to request services and access resources. That's where system calls come in. Think of system calls as the interface between user programs and the kernel. When a program wants to do something like open a file, read from the network, or even just print something to the screen, it makes a system call. The kernel handles the request and sends back the results. Now, implementing system calls involves setting up a well-defined interface that both the kernel and user programs can understand. We'll need to define things like the calling convention, which is just a fancy way of saying how we pass data back and forth, and the error handling mechanism, so we know what went wrong if something goes wrong. We'll start with the basics. Things like opening and closing files, reading and writing data, and exiting a program. These might seem simple, but they're the building blocks for everything else. Once we have these down, we can start adding more complex system calls like networking and process management. System calls are the bridge between the user space and the kernel space, allowing us to build a secure and reliable operating system. It's all about defining clear boundaries and providing a robust mechanism for programs to interact with the underlying hardware. Okay, we're getting somewhere. Our kernel is running, we've got system calls, but there's one crucial thing missing: hardware support. Right now our OS is basically trapped inside a box, unable to interact with the outside world. Time to fix that. We need to write drivers. These are like little translators that allow our OS to communicate with all the different hardware components in our computer. We're talking about everything from the keyboard and mouse to the graphics card, network interface card, and storage devices. Writing a driver involves understanding the specific hardware we're trying to control. We need to know how it works, what commands it understands, and how it reports back to the system. This often involves poring over data sheets, which are like the instruction manuals for hardware. We'll start with the essentials. We need a driver for the keyboard so we can actually type commands, a driver for the display so we can see what we're doing, and a driver for the storage devices so we can load and save files. Once we have the basics covered, we can start adding support for more specialized hardware. Writing drivers can be challenging, but it's also incredibly rewarding. It's like solving a puzzle, figuring out how to get all the different pieces of hardware to work together in harmony. And once you've written a driver, you'll have a deep understanding of how that particular piece of hardware actually works. Our OS is coming along nicely. We've got the kernel, system calls, and drivers, but it's still pretty bare bones. Right now, the only way to interact with it is through a bunch of cryptic commands. If we really want to impress our friends, we need to give our OS a face, a user interface. Now, we could keep things simple and stick with a command line interface, or CLI. This is the classic way of interacting with an OS, typing in commands to tell it what to do. It's powerful and efficient, but it's not exactly user-friendly. If we're feeling ambitious, we could go all out and create a graphical user interface, or GUI. This means windows, icons, menus, the whole shebang. It's a lot more work, but it makes our OS much more approachable for everyday users. Building a GUI involves creating a windowing system, which manages the display and handles user input. We'll need to create windows, draw graphics, handle mouse and keyboard events, and a whole lot more. It's a complex undertaking, but luckily there are libraries and frameworks that can help us. We could even get really creative and design our own unique user interface paradigm. Something that's intuitive, efficient, and maybe even a little bit fun. The possibilities are endless. Okay, so we've been writing a lot of code, and let's be honest, there are bound to be some bugs lurking in there. That's just the nature of the beast. But fear not, brave OS developers, because testing and debugging are here to save the day. This is where we put on our detective hats and start tracking down those pesky errors. We'll be running our OS in our virtual machine or emulator, poking and prodding it, trying to make it crash. The goal here is to find the bugs before our users do. Now, debugging an OS can be tricky, especially since we're working with low-level code, but fear not, there are tools to help us. We can use a debugger like GDB to step through our code line by line, inspect variables, and figure out what's going wrong. We can also use a tool like QEMU, which is an emulator that allows us to simulate different hardware configurations and debug our OS in a controlled environment. And if things get really hairy, we can always fall back on the trusty old serial console, which lets us communicate with our OS even if the display isn't working. Testing and debugging is an iterative process. We find a bug, we fix it, we test again and repeat. It can be frustrating at times, but it's also incredibly satisfying to finally track down that elusive bug and squash it for good. Congratulations! We've got a basic operating system up and running. It's probably not going to win any beauty contests just yet, but hey, it boots. But the journey doesn't end there. Now comes the fun part, iterating and adding features. This is where we get to unleash our creativity and build the OS of our dreams. We can add support for new hardware, implement advanced features like multitasking and networking, and even create our own custom applications. We could start by adding support for a real-time clock, so our OS knows what time it is. Then we could add support for networking, so our OS can talk to other computers on the network. And if we're feeling really ambitious, we could even try implementing a basic web browser. The key here is to start small and build up gradually. Don't try to do everything at once. Pick a feature you're interested in, break it down into smaller, more manageable tasks, and then tackle them one by one. Remember, building an OS is a marathon, not a sprint. It's going to take time, effort, and a lot of caffeine, but the rewards are well worth it. So keep learning, keep experimenting, and most importantly, keep having fun. We've poured our heart and soul into building this OS, and it's starting to look pretty impressive. But what good is all this hard work if we don't share it with the world? That's right, it's time to document our code and share it with other like-minded individuals. Documentation might seem boring compared to writing kernel code, but trust me, it's crucial. Not only will it help others understand how our OS works, but it'll also help us remember what we did months or even years down the line. Plus, good documentation can turn a good OS project into a great one. We can start by writing clear and concise comments in our code, explaining what each function does and how it works. We can then create a dedicated documentation file, outlining the overall architecture of our OS, the different components and how they all fit together. And hey, why stop there? We can create a website for our OS, complete with a download link, installation instructions, and even a user forum where people can ask questions and share their own experiences. Who knows, we might even inspire others to embark on their own OS development journeys. Sharing our work is not just about showing off, it's about contributing to the open source community. It's about learning from others, getting feedback on our code, and maybe even inspiring the next generation of OS developers. So let's get out there and share our creations with the world. So there you have it. You've journeyed into the depths of operating system development, learned a ton, and hopefully had some fun along the way. Remember, building an OS is a massive undertaking. It's not something you do overnight, and it's definitely not for the faint of heart. But hey, you made it to the end of this video. And that means you're not afraid of a challenge. Start with small, manageable projects and gradually work your way up to more complex tasks. There's a whole world of resources out there, from online tutorials to open source OS code bases just waiting to be explored. Don't be afraid to dive in, get your hands dirty, and learn by doing. And most importantly, have fun with it. Building an OS is an incredibly rewarding experience. So go forth, code like the wind, and who knows, maybe one day I'll be reviewing your amazing OS right here on this channel. Until then, keep on creating.